computer, yes. And over here. Okay. Nobody else wants in. There are 9 of you out there maybe listening. And 2, 5, 10 people here, so only missing 4 or 5 for whatever that tells us. Okay, I wanted to go ahead and do the last 2 examples that we kind of just mentioned yesterday and didn't do because it's my opinion, the author, sometimes I complain, but right now, the author, this section, he does a good job of giving you some varieties of things to do, none of which are too hard, but each of them illustrates some aspect of the kind of thing you can expect, at least in this section. And I see this is beginning to needs cleaning. Okay, the car is traveling west at 50 miles an hour and so forth. And so we're going to draw a picture on the screen, on the board here. Some of you. And so basically you've got one person going this way and one person going this way. And so this person's going 50 miles per hour. This person's going 60 miles an hour. We'll write down more about that in a minute. Both are going for the intersection. And the question is, at what rate? Now, that's a derivative. At what rate, okay, of something. And it says, are the cars approaching each other? So I'm going to just say between because approaching is too long a word. Between the 2 cars, A and B. So you name the cars A and B. Car A is up here and car B is down here. And what rate between them, okay, how is it changing? He says, when, now we have 3/10 of a mile for A, so I'm going to have a 0.3 away, and here we're going to have a 0.4 away. And so far I don't know how to write that all down. I'm just kind of putting it down so we can see something. And so what are we going to do again? Well, yesterday, yes. Yes, I see that. Thank you. Yesterday, Sean wants to come in. Okay. Yeah, okay. Yesterday, we labeled the size of things. We had ladders and stuff. So I'm going to still do the same thing. And it doesn't matter what we call things, but normally if people like to call things on that, like an x-axis, maybe with the letter X, and y-axis, maybe the letter Y. What it means basically is that it's the distance from the car to the intersection. Okay, so it's this whole distance. Now, I wrote 0.4 here. Is 0.4 what I want to say equals Y? No. No, because it's only at one time. Okay, so in a sense, we have a second picture. If you took a picture at a certain time, this would be time t0. If there's a helicopter up above taking a picture down below, at some time it would be accurate to place the 2 cars in those positions, but that wouldn't be true all the time. So what do? I introduce a time and I say, okay, X of t0 is 0.3 and Y of t0 is 0.4, I guess. Okay, so I can erase these kind of help because they kind of confuse me instead of help me. Okay. Now, should one of them be positive and one of them negative, or I don't know. We have to think that out a little bit. Okay. Except this is just how far you are away. Right? Do we need to worry about whether you're going north or south or whatever? I don't know. But these are just a distance. And what about, maybe it's the speed I need to worry about. Because the speed is 50, I guess. But the derivative at all time is maybe 50. I said maybe, but why am I saying that? Because they say the car is traveling along the road. That's a constant speed. Now, speed and velocity are different. Speed is the magnitude of velocity. In this case, the car is going at a constant speed. So when we think that, the magnitude of the velocity is the speed, but basically they're both going 50 all the time. And so some people think the velocity is 50. Now, actually the velocity is either positive 50 or negative 50, depending on direction, which we may or may not need to think about. So the other one is y prime. That was 60. Okay, now, do I need to worry about what the number means compared to the change of distance? Now, do you all understand what I meant or tried to say there? The distance to the intersection is getting shorter. Should that be reflected in the sign of the velocity?
I would say yes, because I would kind of which way you
It
go.
should be reflected.
Yes.
Okay, so should it be 50 and 60?
Yes, it's to
You mean negative,
well,
because
Should be
it is-
negative 50 and negative 60.
because it is,
no, it'd be, what if it be increasing?
Well, I don't know, I should take this class.
Wouldn't it be increasing?
Everybody thinks that's true. Anyway, so maybe, okay, well, at least this seems to be a question, right? And should we worry about that? Now, so let's see what we can do. What's the distance between them? It's this, right? And so the distance between them would be x of t squared plus y of t squared, because again, we have a right triangle, equals, now, when we had a ladder, we knew it was 10 feet in that first example. I don't know what this is, so I'm going to call this distance d, but again, I don't want to call it a constant because it's not a constant, so I'm going to call it a function of t. So I have three functions of t, three letters this time, none of which do I necessarily know what they are, but I have a relationship between them that is true for each t. Okay? In order to determine any one of them, I'd have to know what the other two of them are. But do I need to know that? And the answer is no. I need to know something at one time only. Now, can I replace anything yet? Can I replace x of t equals something? And the answer is no. But I can differentiate. Now remember, yesterday I differentiated. I had 2 x of t, x prime of t, and 2 y of t, y prime of t. And it was 0 yesterday. And I think Mr. Lammers asked me about that. I think.
yes.
In any event, we had yesterday a 0, and the question was, what happened to the 2's? And I said, well, when you have this situation, you could divide by 2. However, this time I don't have a constant, so I got to be careful when I divide by 2. However, since this is squared, when I differentiate, I'm still going to get d of t, d prime of t. And so this time I've got 2, 2, 2, again, all the way across. So I still could divide. But it's different because now I have a 2 on the right-hand side as well, which I have to remember to get rid of if I'm getting rid of 2's. So if I do that, I have x prime of t and x and so on. Now, can I, for this equation, get rid of anything?
Yeah, you can go with the prime t and y prime.
Yeah, this is always, these are always. So I can write 50 plus or minus, you got to worry about. 50 x prime of t, no, x of t times 50 plus y of t times 60 equals D of T, D prime of T, I guess. Yes.
Someone whose phone died and
Ah.
fell out of the meeting.
Oh, somebody's mad at me, probably. Ibrahim, you are now legitimate. Not a question of birth. I'm staying away from that. Okay. Choking. Is that okay? I got to worry about minuses maybe, but I'm trying to put in the things I'm given into the problem. What am I trying to find out? I don't know. Trying to find out, what was the question? How fast are they approaching? What rate are they approaching each other? When? So I didn't write that down. What I'm trying to find out is D prime of T naught, right? That's what I'm trying to find out. So I have a formula for D of T for all T. If I would put T naught in here, and again, I'm still worried a little bit about those 50s and 60s, but if I put in the T naught in here, I have D of T naught, D prime of T naught, and now I finally have the thing I don't know in an equation that hopefully I can solve. Now, because I have substituted T naught, this is information I was given, so I can put that in now. So I have 50 times 3/10. So I got to figure that out. I don't have my calculator. Shoot, on my calculator I could do this. 50 times is 150. 10. That's 15 times 10. 10 times 1. Yay! Now, I am hoping that you don't have to do all of that. Okay? First of all, when you're doing something in your head, never multiply it out. Factor first. When you multiply it out, you get big numbers. When you get big numbers, you make big mistakes. Okay? With little numbers, you make little mistakes. Always better. So what I would have done here in my head would have been to cancel this and get 15 right away. So that means up here, I can write 15. Now there's a question about the sign, and the next one, I have 4/10. 4/10 times 60. I hope, at least in most countries, is 24. I still have a problem with the sign, maybe. What's D of, I've got something that nobody gave me. I don't know what this one missing is. But over here in this picture, this was this thing from the helicopter, remember? The snapshot. At one time, we can figure out this distance. And I'll bet it's 0.5. And that's because 16 over 100 plus 9 over 100 is 25 over 100, which is 1/4. Oh, why isn't this 0.5? Or is it? What's the square root of 1/4, which is 1/2? So it's okay. But you will get yourself confused. That's why you always calculate it. But you should, anyway, it should be 0.5, I believe. And if it is, then I put 0.5 here. I put 0.5 here. Is that the distance between them?
Possibly.
This is 0.3 miles. This is 0.3 miles. 0.5 miles. So, what do you think? Are we doing this problem correctly?
I think so.
Okay. Except the book's got minuses. But anyway, if we do this, let's see what we get. This is 15 and 24 is 39. 39 divided by 1/2, that's 0.5, you know. I get 78. I Be a 78. What's the book get? If you look at the book on page 184, the book gets minus 78. So I put this little question mark, but I need to kind of maybe think about worrying about this. If you do not put in the minuses, because both distances are decreasing, you're going to get a derivative which is positive, but you have to interpret it as decreasing. Like, because you're saying 50, okay? Well, what we're saying over here is 78, okay? But in terms of decreasing, it should technically be minus because it's changing in the negative sense, okay? You're getting shorter. So what we should have done is put a minus here and a minus here, and shouldn't have been unexpected to find a minus here. But if you know that, you don't have to do that as long as you interpret the answer correctly.
Why it's 38 and not 79? Because
Well, slow down. 39 times 2 is 78.
oh,
Okay. Might be different at your house. I don't know. Okay. So that's how you do that problem, kind of, again, stumbling over it and stuff and just trying to think it out. So again, what I'm trying to do is to think about some stuff that you might think about. I don't know. Maybe you should. Okay, now we got this man walking a straight line, a straight path along a wall at a certain speed. The searchlight is located on the ground 20 feet from the path. Okay, so now, you know, because of not wanting to waste chalk, I can use the same picture. Except this time we got a guy walking the other way, and his distance is getting greater as he walks from the place where they're measuring the distance to the searchlight, which is here. Okay, and so the searchlight this time, and we're back to feet. The searchlight is 20 feet from the point of nearest place on the wall, and the guy's walking at 4 feet per second. Okay, so this is 20 feet here. That is not going to change because the searchlight is fixed, as I believe. But the guy is changing. Now, this 4 feet I can interpret as positive 4. And by the way, is 4 feet per second very fast? 88 feet per second is 60 miles an hour. So if you divide by 10, 6 miles an hour would be 8.8 feet per second. So he's walking about 3 miles an hour or something like that. That's not very fast. You all can do that, I think. Okay? Sometimes people lie with figures, you know, especially in the political time. But I remember in my life, and this is not political, but I remember in my life, it might be considered by the country I'm going to name to be political, but it's not. There was a time when a certain ruler of a country, so I won't tell you the country, because you'll know. A certain ruler of a country in the newspaper said he was dead. And I'm not talking about rather recently. Rather recently, there was a question about whether the chairman in North Korea was dead. I'm not talking about that. I'm talking about 30 years ago. Okay? Somebody was dead, supposedly. And this came out in all the Western newspapers, because this was an Eastern thing. All the Western newspapers said, this ruler is dead. The country came out and said the ruler is not dead, the ruler is perfectly healthy. And they showed a picture of the ruler swimming in a river, exercising. Okay? And they said this particular guy, the ruler, swam from point A to point B like in an hour to show he was healthy. And so they had a video of this showing the guy swimming to prove to everybody that this was a healthy ruler. Yep. The trouble was that the distance, they said, for the hour was 60 miles. That he was swimming 60 miles an hour. Okay? So rather than dispel rumors, because this guy was like 75 or 80 years old, so rather than people believing that this guy was actually, nobody believed it, and it just made it worse. Because evidently some idiot wrote the wrong calculation about how fast this person could swim. Anyway, but this is not too fast. But so what? That's not the question. That's just wasting time. What are we supposed to be doing? We're trying to find how fast the searchlight is revolving. So that must involve an angle. I'm going to make myself an angle. And the angle, maybe not in the book, but for me, the angle is a function of time because it's changing. As the guy walks further, the angle gets greater. Okay. And they want to know something about, what's this question? At what rate is the searchlight rotating when the man is 15 feet? Okay, so I'm going to have x of t naught is 15. So again, my time is t naught, and x of t naught is 15. And what do they want to know? They want to know how is this is maybe what they want to know. How is the angle changing at this time? Okay, maybe that's what they want to know. We got to think that out. Okay, so the author sets this up, and he says we are given the ds dt. Now, a lot of times when we talk about position, instead of using x, we use s, and the book is doing that at this time. Okay, except the book is saying s is s of t. In other words, the book's not using functions, it's using variables. But anyway, when you get ds dt, that's what the book is calling the derivative. That's fine, but that makes s the function, not the variable. And normally what we do here is we have a variable, and I would still call it x of t. It doesn't matter as long as you get things straight and you use the good notation. So s prime of t is 4, and he's asked to find d theta dt. That's what I said. When x is 15. So for the author, he has to write find d theta dt when x is so and so. That's all said by these two facts right here. X prime of t naught is 15, and find theta prime of t naught. That's what we're supposed to do. So how can we relate the x, which we know? See, the 20 is 20. This is 20. The distance to the person, you might want to know about that, but it doesn't ask about that. It just asks about this angle. So in this case, although we could figure out the distance between them and how long it's getting in terms of how far the searchlight has to go, then you have to worry about these things with flashlights, because after you get too far away, it doesn't show on the person anymore. Things like that. People worry about such stuff. At least I do when I'm in certain places. But I can do a relationship here with number, and angle. Namely, the tangent of the angle is the, what is that again? It's the opposite over the adjacent, I think. That's what we call that? We call that x of t over 20. And this is true again for all t. Okay? Assuming that t starts at 0, because that's where we are calibrated. So what do we do to find, because we're given x prime of t, we're not given x of t. So we differentiate. Derivative tangent, you should know by now, is the secant squared. but I'm not just differentiating with respect to theta. If I was differentiating with respect to theta, this would be done. I'm differentiating with respect to t, so this is a composite function. So I now have to multiply by the derivative of the inside, which is theta prime. Over on the right-hand side, it's x prime, and the 20 just stays as a constant. So my new formula is the secant squared of theta of t times theta prime of t is x prime of t over 20. Now, what can I get rid of without evaluating the time? Well, someplace or other, we're told that this is going on all the time. Therefore, I can rewrite this up somewhere as the secant squared of theta of t times theta prime of t is equal to 4 over 20, 1 over 5. That's because of this information. That's for all time. And now I want to get into the certain time. This is t naught, and I have theta prime of t naught, and this is 1/5. So at a particular time t naught, I have the same formula, except now I have t naughts in it. Part of the thing I have written is what I want to know. That's why I write down what I want to know, so I know later when I'm getting close. I want to know this right here. So one answer, theta prime of t naught is 1/5 of the cosine squared of theta of t naught. Because if I take the secant squared to the other side, it becomes the cosine squared. And maybe I don't know anything else. Maybe I'm stuck with this. But I'm hoping that I can figure out what the cosine or the secant is. Okay? So what do I need to know to do that? I need to have a snapshot of what's going on at the certain time. Okay? So, what's x of t? Is there some way I can figure out this is theta of t naught? And so that's what do I know with that? This is 20. This is 15. Yes, at t naught. This is theta of t naught. Can I find the secant? What's the secant? It's the adjacent over the hypotenuse. Can I find the hypotenuse if I know two sides?
Yes.
Yeah, it's the sum. So this is 225 when I square it. This is 400 when I square it. 400 plus 225 is 625, which happens to be 25 squared. So this turns out to be 25. And that's the thing I need to know. So what's the secant or what's the cosine? Either one. The cosine of this angle is adjacent over hypotenuse. That's 4 over 5. And so it's 4 over 5, I guess, squared. And so I'll get 16 over 125, I guess. I don't know. Just a minute. Wait. I got what the book got. That's exciting. Sorry?
Why would you use the cosine if the question asks for secant?
Okay, well, okay. The secant squared of anything, of alpha, okay, is 1 over the cosine squared of alpha, because they're reciprocals. So if I have this times x equals y or something, and I change it to this, I can multiply by cosine squared on both sides. Because in the denominator here, I'll multiply through, it becomes a numerator. If I think of secant squared as 1 over cosine squared, when I move over there, it goes up in the numerator. Okay, so these are the 4 examples, or 5 examples, which I hope taking time is helpful to you guys, not wasting time. I'm hoping And you can look and see exactly what the book does and decide whether you like that better. I personally think it's worse, but that's just an opinion. Okay? The person who wrote the book is certainly an able, or was, he's dead now, but was an able mathematician. When you look at some of the WebAssigns, the guy you see in those first kind of things in your assignments, you see a video. That's the instructor, that's the professor. He's Canadian, but that doesn't mean he's a bad person. So unfortunately, he's no longer with us. But his book is. Now, there are 50 word problems to do. And I don't really want to do any right now, because I just talked my way through some, and we've only got 17 minutes left. But you need to pick out a few and try them. Okay? Now, I don't know if I yet made an assignment. I think I did put the things on WebAssign. But basically, if you just read some of them, I think you'll find some of the things are kind of interesting. Just the statement, not the answer, but just the idea. Like the baseball question I found. And there's some fairly, I think, interesting things. And one thing to do, even if you don't work the problems, is see what we're beginning to be able to solve with calculus. Okay? There are life problems in life out there that people solve, and certainly we're not very far along the line, but we can still solve several kinds of problems here of different varieties. And I think if you read through it, well, you might think, hey, I'm actually making some progress. And this is mainly for people who haven't had calculus before. And I don't know if you guys have ever climbed much in mountains, let's say, but if you, let's say, go to Estes Park, Rocky Mountain National Park, for example, there are trails that you can take, and basically they climb up to certain altitudes that are higher than the altitude in the parking lot. And what you'll see in the morning is people who get all geared up with their backpacks and this and that at the parking lots, and they're all enthusiastic about climbing and so on. Now, if you go up, because I'm an observer, if you actually climb up before they do, let's say climb for maybe 10 or 15 minutes before the people in the parking lot do, and then watch them come up the trail, okay? Most of them are not in very good shape. And so what you'll see them start doing is thinking about stopping. And sometimes they don't get much further than that. I know people who decide they're going to go back to the parking lot. Anyway, but if I were a guide at that moment, when somebody feels like they've gone about as far as they can go at the moment, and they're out of breath and so on, and by the way, in such a place like Rocky Mountain National Park, you're up about 6,000 feet, and so it is different than living in Wichita in terms of how fit you are. You have to get used to the altitude. But anyway, if I were a guide, what I would do is tell them, okay, you've been walking, I know you're tired. Look how far you've come in 5 minutes. And if you look down, the parking lot is way below you. But unless you see that, you won't think you went very far. But most people, when they see how far, what the altitude they actually have gotten to, makes them think, oh, that's pretty good. I didn't realize I had climbed as much as I did, even though I thought I was dead. Okay. Now, the other thing, if you do go to Estes Park and you want to pick up a lot of equipment, what you want to do is go up on the road that crosses over the Continental Divide, because when you get up fairly high, there are some lakes down below, and people like to climb down to the lakes. The problem is this is an extremely strenuous activity. And so what people do is they climb down, but they're unable to climb back up, and so they leave all their gear down at the bottom by the lakes, because they're too heavy to carry back up. So if you'd like to collect a lot of gear, you just go down to the lakes and collect all the gear, because they'll never come back.
How are you getting that?
Well, that's a different problem. And that has to do with how people used to catch monkeys. What people would do is put food behind something that you could put your hand through, but if you closed your hand around something, you couldn't get it back out. See? And the question is, when you come upon the animal wants to leave, but the animal doesn't want to let go of what it's. And sometimes you catch the animal that way because they won't let go, even though it captures them. Anyway, maybe you can find the relevance of that. Okay, so what is in the next section? Not just trying to push sections at you, but I want you to get familiar with this chapter. Next section is linear approximations and differentials. And so in the time we have left, I just want to talk a little bit about notation. So it's not new, it's just sort of new. It's sort of like, oh, I hadn't realized or something. That's what we're going to talk about. Okay, so where did the notation originally come from that involves derivatives? Well, people have y equals f of x, and sometimes we say the following: dy over dx is the limit as delta x goes to 0 of f of x, and I'm going to do this. And so this is what you'll see sometimes. And what it involves is the idea that I'm at some place x. Now, as you have gotten to know, I don't like x, I like x naught. But this is what a lot of people do. So they write x, and then they're going to go a distance delta x, and delta x doesn't have to be positive, but again, I'm making up the picture, I'm just going positive. So this point is x plus delta x, and you go up here and you say, okay, what's going on up here? This is the x part is x plus delta x, and the y part, that's f of x plus delta x, okay? Pair of them, and this point is x f of x. So what is the line in between is called a secant line. Now, also, people call this, if this is delta x, people call this delta y, but not exactly. Let me make it a little bit better. They call delta y the distance here. So what you get is delta y over delta x. One's a vertical, one's a horizontal, and when you divide one by the other, you get what's called a slope. And since it's a straight line, the slope's not changing. This is called the slope of the line. So when people were first doing this, they took ratios of this. So now, if you look carefully at what I wrote here, that's delta y. Because it is the difference of the y values, where this y value is x plus delta x, but it's only up f of x. So the difference of the two things I'm underlining here, that's the difference in heights. And that's called delta y. The difference in x's, that's called delta x. And so what I'm writing here basically is what some people learn when they learn derivatives. Okay? Now, this notation is meant to be like a stamp. It's not meant to be a quotient. It's not meant to be a fraction. It's meant to be a symbol. Okay? But people sometimes mess that up. They forget that. So let me go over and do something a little different. Now, I'm going to write it what I like better. So I'm going to talk about f of x naught plus h minus f of x naught over h, and I'm going to let h go to 0. Now, I hope you see I haven't done anything different in terms of the idea here. I'm writing H instead of delta X. They're both just numbers. And I'm writing X naught instead of X because I like to fix the place at X naught instead of X. I wouldn't have to do that, but there's reasons why I want to do that. So I'm evaluating because these are not formulas, these are numbers. This is a number, a height, this is a number. This is still what would be called delta Y, if you like. Except I'm just naming this X naught and I'm naming this H. And once you do that, it's the same thing. Okay? But I'd like to call the answer, the derivative, by this name instead of the other name. Now, when I write it this way, you don't see any quotients. You just see a thing, okay, a symbol. Okay, now, we produced, if you look in the notes in the right places, this is true if and only if, I hope I have time to say all this, it's getting to be, oh, I still got some time. Good. This is getting to be something you're supposed to know, namely I can subtract the F from both sides and I can change things into this because this is a constant. The limit of the constant is just itself. So I can take the constant inside. We've already talked about that in my notes and we talked about it before. Now I'm going to make a common denominator. Make a common denominator. And out. Okay. And I can do that with this notation, but the notation begins to cause trouble. So the understanding will come from here, and then hopefully we can play with the other one. Anyway, this is what could be a totally equivalent way to define differentiability. We could say a function f is differentiable at x naught if this limit is 0, because they're 100% the same. Okay? Now, if I look at this, and we may have talked about this already, but if I look at this thing here, the f of x naught, if you allow me, if everybody sees this now, I should write another line, but I'm beginning to run out of time. What I want to do is put in a bracket here, and put in a bracket here, and make this plus. So instead of having minus minus, I want to have minus the collected thing. All right? So I change this sign. And if I now look and see what I've got, okay? I've got this in brackets, and over by itself, I have this. So I've got two different things here now, both in the numerator. What is this thing? This thing, I don't have the picture, but this is x naught plus h. That's the height here. This is the f of x naught plus h, the whole height. And what is this? This is this height, f of x naught, plus this amount. Okay? So, I mean, again, in that other notation, this was a delta y. So, what I'm doing is this limit of this quotient. Now, the denominator is going to 0. You guys are like, when the denominator goes to 0, you're like, it's sort of like you feel bent on saying the derivative doesn't exist. But every derivative, the denominator goes to 0. So anyway, what happens for a limit for the quotient to go to 0? The numerator has to go to 0 faster than the denominator. If they go at the same rate, you got like sine x over x. Sine x over x goes to 1. If you look at the graph of sine x and x, you'll see they're almost identical, near to 0. When you divide something by something almost identical, you get 1. If I get 0 and I divide, what happens? This is going to 0. This is going to 0 as well. but this has got to go to 0 much faster than this does to make the quotient go to 0. That make sense? So this thing in brackets is very close to this thing. So this thing in brackets approximates this thing. Well, if I would set this equal to y and write it down, I get y is f of x naught plus f prime of x naught times h. And that, if instead of h I write x minus x naught, that's the equation of a line. And it's a line that passes through this point right here. And so what this is, this part I'm approximating the function with is a line. And it's called the tangent line. Now, I'm hoping the time, I mean, we're going to have to pursue this a little bit later. But what people do, because what they did is they called the h delta x. And so what I'm trying to tell you here is people got this notation because the h is a number and the delta y is a number, and neither of them are 0 necessarily. And so I'm equating them. If I equate them, I get delta y is a number times delta x. Okay, now I prefer h, but never mind. And people thought of the delta h, because it's a limit, as being very small, the delta x. And so it was called an increment. It's just a little bit, very small positive number. And so what you get here, since this is a number and this is a number, if I divide one by the other, I get this. Yeah. Now, so I get that the derivative is a fraction. Now, the mistake people make is over here when we call dy dx f prime of x, the derivative notation. Now, this is a symbol. This is not a fraction. Okay? But it equals f prime of x. That's what people do. Over here, I have delta y over delta x equals a derivative. But I've got an x naught in here. The reason I like x naught is because if I take it off, then it looks like that derivative symbol over there. The originators of calculus thought that this thing became something else when the delta x got small. They're wrong. I mean, in other words, it doesn't become a fraction. But you see a fraction here as a derivative. Over here, you see a symbolism that looks like a fraction. So because people confuse f prime of x, a function value, with f prime of x naught, a number, all right? People learn that this thing stands for derivative, and then they write dy is f prime of x dx. And they think they got it from what I just did. And when you write this, the dx is called the differential of x, and the dy is called the differential of y. Now, for us right now, this has absolutely no meaning yet, because it is incorrect to get this formula from this work over here. Okay? Now, I'm running out of time. But historically, they didn't have functions, and so they didn't know that these two things are different. So they put them together, and they thought that derivatives were actually fractions of very small quantities. They were called infinitesimals. And it's all nonsense, mathematically. But the inventors of calculus were so smart that they made nonsense correct, or made it work, made you get correct answers with nonsense. Sort of. Okay? I'm not trying to be mean to the people. They're geniuses. And they knew what they wanted to get, and they forced it to go there. They forced a round peg in a square hole and fit, you know? I saw a TV program the other day where a woman was building a puzzle, a interlocking puzzle. And she was trying to fit a piece into the space and it didn't work. So she picked the piece up, took her scissors and cut on it and put it back in, and then it worked. Okay? That was in some movie I saw. And I thought, that's interesting. Okay. Anyway, I'm going to stop the recording because some of you got to go and stuff. We will talk more about this. The reason that, where's my recording?